Good morning. Today we are going to discuss about eddy current and self-induction. Under eddy current, you are going to learn what is eddy current, the experiment to demonstrate eddy current, the losses in eddy current, how to reduce eddy current, and the uses of eddy current. What is eddy current? Eddy currents are induced currents in bulk piece of conductors when they are subjected to changing magnetic flux. The flow pattern of these currents resemble swirling eddies in water. They were discovered by Foucault in 1895 and also called as Foucault currents. This is based on the phenomenon of electromagnetic induction. Before starting, let us have a recap on coil and magnet experiment. You have already studied that when the north pole of the magnet moves towards the coil, the magnetic flux linked with the coil increases. And when the magnet moves away from the coil, the magnetic flux linked with the coil decreases. So, whether there is increase or decrease in flux, it is a kind of change in flux. According to Faraday's law, we know that any change in flux will lead to induced EMF or induced current. Now, let us replace the coil with a conductor or a disc. If this conductor is moving in an external field, then a current is generated in the conductor. Or, if we vary the magnetic field by keeping the conductor fixed, then a current is generated. The electrons in the conductor will be moving in a circular manner inside the conductor. This is called circulating current. The flow pattern of these currents resemble swirling eddies in water. So, they are called eddy current or Foucault current. You can see the swirling eddies in water in the second picture. Now, let us allow the conductor to oscillate in the absence of magnetic field. Then, we can observe that it oscillates for some time and finally comes to rest. If we apply a magnetic field and allow the conductor to oscillate, then it will oscillate for lesser time compared to the oscillation in the absence of magnetic field. This is because eddy currents are set up due to the oscillation of the conductor in the magnetic field. The eddy current tends to oppose the motion of the conductor and finally brings it to rest. This kind of opposition offered by the eddy current to the motion of the system is called electromagnetic damping. Note that there is no magnetic damping on a non-conducting plate. You have also studied that when the north pole of a magnet moves towards the coil, a current must be flowing through the coil, and the current flows in such a way that it opposes the cause that produces it. So, the near end of the coil will behave like north pole. Similarly, if north pole of the magnet moves away from the coil, then the near end of the coil behaves like south pole, so as to oppose the cause of it, which is in accordance to Lenz's law. Next, we will be moving to experiment to demonstrate eddy current. Look at the figure. Consider a conductor oscillating between pole pieces of an electromagnet. When the conductor moves towards the magnetic field region, that is, the region between north and south pole of the magnet, its flux increases. So, due to the change in flux, the electrons inside the conductor will start circulating and will create eddy current, and this will oppose the increase in flux. So, the face of the conductor towards north pole of the magnet will behave like north pole, and the current will be flowing in anti-clockwise direction. Now, when it oscillates and comes out of the field to the other side, the flux decreases. According to Lenz's law, the induced EMF opposes the change in flux. So, to oppose the change in flux, the conductor will be pulled inside. Now, the face of the conductor towards north pole of the magnet will behave like south pole, or the current will flow in clockwise direction, so as to oppose the motion of the conductor away from the magnetic field region. Hence, eddy currents opposes the motion of the conductor, and finally the oscillation comes to rest, which is nothing but electromagnetic damping. Next is disadvantages of eddy current. We know that P is equal to I square into R, or P is directly proportional to I square, where P is the power, I is the current, R is the resistance of the conductor. If current flows through a conductor, power will be generated and heat will be produced. So, when the coil is oscillating, eddy current will be circulating in it. Hence, power will be dissipated. So, the two losses are heat loss and power loss. Next, we will be seeing how to minimize eddy current. Look at the figure. To reduce eddy current, the conductor should be cut into a number of slots, and each slot should be laminated. So, the area for circulating current decreases. Also, you will learn the equation R is equal to rho L by A in current electricity chapter. So, look at the relation. When area decreases, the resistance increases. And when the resistance increases, the current decreases. When current decreases, power loss also decreases. Next, we will see about the uses of eddy current. The first application is magnetic brakes in train. Second is electromagnetic damping. Third is induction furnace. Fourth is speedometer. Fifth is electric power meters. And the last one is induction motor. So the first application is magnetic brakes in train. Nowadays, train have electric brakes in addition to usual vacuum brakes. Coupled with the wheel of the train is a metal drum which rotates as the train is running. Strong electromagnets are situated near the metal drums. When the electromagnets are activated, eddy currents are set up in the drum, which opposes the motion of the train. As the speed is reduced, eddy currents are also reduced, and the braking action becomes smooth. The next application is in electromagnetic damping. This is used in galvanometers. These galvanometers have fixed core of non-magnetic metallic material placed between the pole pieces of a strong magnet. When the coil oscillates, eddy currents are generated in the core, which opposes the motion and brings the coil to rest quickly. The next application is in induction furnace. Induction furnace, it is used to produce high temperature and can be utilized to prepare alloys by melting the constituent metals. A high frequency current is passed through the coil surrounding the metals to be melted. The eddy currents generated in the metals produce high temperature sufficient to melt it. The next application is, it is used in speedometer. In speedometer, a tiny magnet rotates according to the speed of the vehicle and produces the required changing magnetic field. The magnet rotates in an aluminium drum. The eddy current setup increases as the speed of the vehicle increases. Using calibrated scale, the speed of the vehicle can be obtained. The next application is, it is used in electric power meters. The meters used to record the consumption of electricity makes use of eddy current. And the last use is It is used in induction motor. In an induction motor or an AC motor, a rotating magnetic field produces strong eddy currents in a rotor. The rotor starts rotating in the direction of rotating magnetic field. Thank you. You can see the video attached. Now, we are moving on to the next topic, that is self-induction. Under self-induction, we are going to study the following: definition and explanation of self-induction, coefficient of self-induction or self-inductance, definition of SI unit of self-inductance, expression for self-inductance of a solenoid, and expression for energy stored in an inductor. Before starting, let us understand what is meant by a solenoid. A solenoid is a long, thin loop of wire often wrapped around a metallic core which produces a magnetic field when an electric current is passed through it. Or, a solenoid is a tightly wound helical coil of wire whose diameter is small compared to its length. The windings are sufficiently tight that each turn of the solenoid can be considered as a circular wire loop. The magnetic field generated in the center of a current-carrying solenoid is uniform and is directed along the axis of the solenoid as in the figure. The expression for magnetic field inside a solenoid is given by B is equal to mu 0 Ni by L, or B is equal to mu 0 small n into I, where small letter n is equal to capital N by L, which is the number of turns per unit length. This expression you will be learning in chapter 4, that is moving charges and magnetism. In this expression, mu naught is a constant and it is known as permeability of free space, and its value is 4 pi into 10 power minus 7 newtons per ampere square. Capital N is the number of turns in the solenoid, capital I is the current in the coil, capital L is the length of the coil, and small n is equal to capital N divided by L, which is the number of turns per unit length. Note that the magnetic field in the coil is proportional to the applied current and number of turns per unit length. What is self-induction? Self-induction is the phenomenon in which an EMF is induced in a coil due to the change in magnetic flux through the coil as a result of variation of current in the same coil. Now, let us study about self-induction in detail. Look at the first figure. Let us consider a solenoid or a coil connected to a battery and a key or a switch. Let us press the key or the switch so that the circuit will be closed. A closed circuit means current will be flowing in the circuit. When you press the key, it will take some time for the current to reach its maximum value from 0, and then it becomes stable. So, when the current changes from 0 to its maximum value, its magnetic field changes. When the magnetic field changes, the magnetic flux linked with the coil also changes, and it will lead to an induced EMF. This induced EMF will be in the same coil, and we call this EMF as back EMF or self-induced EMF. The direction of induced EMF is such that it opposes the cause of it. That is, here it opposes the growth of current in the coil from 0 to maximum. Hence, we can say that induced EMF is in a direction opposite to the current. You can see the direction of induced EMF in the first figure. Now, when the current reaches a maximum value, the magnetic flux linked with the coil also becomes constant. So there won't be any induced EMF. Look at the second figure. When the key is released, the circuit is opened. The current falls from maximum to zero in this case. Hence, the magnetic flux linked with the coil also decreases. The decreasing magnetic flux sets up an induced EMF in the coil, and the direction of induced EMF opposes the decay of the current. So, it would be in the same direction of the current. You can see that current and induced EMF are in the same direction in the second figure. Next, we will define coefficient of self-induction or self-inductance, capital L. When a current flows through a coil, it sets up magnetic flux through it. The magnetic flux phi B is directly proportional to the current I. That is, flux phi B is directly proportional to I, or flux phi B is equal to L into I, where L is a constant. If current is equal to 1 ampere, then flux phi B is equal to L. Therefore, the self-inductance of a coil is numerically equal to the magnetic flux linked with the coil when there is unit current flow through it. We will now define the SI unit of self-inductance. The SI unit of self-inductance is Henry or capital H. You have already studied that when current in a coil changes, the magnetic flux linked with the coil changes and EMF is induced in the coil. The induced EMF in the coil is given by E is equal to minus d phi B by dt. That is equal to minus d by dt of Li, where phi B is equal to Li, or E is equal to minus L into di by dt. When E is equal to 1 volt and di by dt is equal to 1 ampere per second, then the self-inductance will be 1 Henry. Hence, self-inductance of a coil is 1 Henry if 1 volt EMF is induced in the coil when the current changes at a rate of 1 ampere per second. Let us now derive an expression for self-inductance of a solenoid. Consider a solenoid whose radius is small letter r and length is small letter L respectively, such that r is very much less than L. Let the solenoid have capital N number of turns. If current I flows through the solenoid, then the magnetic field is given by B is equal to mu naught Ni, where N is the number of turns per unit length. The total magnetic flux linked with the solenoid is phi is equal to N into Ba, where N is nothing but the total number of turns, and which is equal to, that is capital N is equal to small n into L. Now we will replace capital N by small n into L and B with mu naught Ni. Therefore, the equation for flux becomes phi is equal to NL into mu naught Ni into A. That is equal to mu naught N square A L I. We know that flux phi is equal to L into I. Therefore, comparing both the equations, we get Li is equal to mu naught N square A L I. Cancelling I on both sides, we get L is equal to mu naught N square A L. This is the expression for self-inductance of a solenoid. Note that if the solenoid has a core of some magnetic material of relative permeability mu R, then the self-inductance L is equal to mu R into mu naught N square A L. Now we will derive an expression for energy stored in an inductor. An inductor is a device which stores energy in the form of magnetic field. This device has self-inductance. We have already studied that the self-induced EMF always opposes any change in current in the circuit. Hence, it is called back EMF. So, work needs to be done against this back EMF in establishing the current. This work done is stored as magnetic potential energy. Let dW be the work done in establishing a current I in the coil in a time dt. So, the rate of work done is given by dW by dt is equal to E into I, which is same as the equation P is equal to VI. Power is equal to voltage into current. Now, let us replace the magnitude of induced EMF E with L into di by dt. Therefore, the above equation becomes dW by dt is equal to L I di by dt, or dW is equal to L I di. The total work done in establishing the current I is obtained by integrating the above equation. Therefore, integral dW is equal to integral Li di with the limits 0 to I. We know that integral dW is equal to W. Therefore, W is equal to L into integral of I di with the limits 0 to I. We know that integral I di is equal to I square by 2 by using mathematical formula. Therefore, W is equal to L into I square by 2 within the limits 0 to I. Now, substituting the value of upper and lower limit, the above equation becomes W is equal to half L into I square minus 0 square, that is equal to half Li square. This work is stored as the energy in the inductor. Thus, magnetic potential energy stored in an inductor of self-inductance L carrying a current I is given by U is equal to half Li square. Thank you.